Okay. Is it okay? Hello everyone, my name is Vilen. I will be giving a short talk on deep learning and our case study with the University of Warwick. So my colleague Rob will give me a hand if you have more questions at the end. So where do we start? 1 second, I can use this, right? Okay, health imaging. Basically, this field is quite diverse and promising. We have a lot of challenges and opportunities here, and among these opportunities and challenges, we can distinguish humongous data volumes being generated by different modalities. Of course, new emerging devices and technologies bring more challenges in storing these images, processing them, pipelining and so on. And also new modalities are getting popularity. For instance, you can see here the 3D tactile image, which is being composed of some preliminary pre-processing of something else, but in general you have many more new modalities, like for instance I can mention something else rather than let's say normal CT scans or fMRI and so on. But in general, these modalities bring new challenges in terms of how do we process this information, pre-process, and then how do we feed these to the deep learning frameworks and so on. So here I also put some of the well-known frameworks in this field: TensorFlow, Torch. Intel also recently acquired Nirvana Systems with its own Neon framework. Also, of course, obviously Theano. Talking more in depth about modalities. So here you can see different modalities being highly popular nowadays, but of course these modalities do differ in applicability. So basically, and in sizes where there is an efficient, basically application-wise utilization of these modalities. So for instance, X-ray, light, electron. So there are different, let's say, from molecule-wide sizes to the whole body. So every modality has its own optimal scale. So what are the challenges in healthcare imaging, and why Intel is actually interested? Obviously, I can mention here that more sizes, let's say more data which is being pumped into the deep learning and into this field generates more compute demanding, more compute demand, more storage demand, and obviously here Intel plays a big role because we provide processors and also storage and so on. But also we can mention here that, for instance, as such known like Holy Trinity, so imaging, omics, and electronic health records are not just only three parts of summed up, but like a bigger picture and like a bigger entity itself. So constitutes most of the, I guess, of imaging being produced nowadays. Sorry. And what are the effective challenges here? So basically, if we talk about deep learning and machine learning frameworks, the scaling of the training phase is difficult because if you have tons of images, you have to pass through the network, through the deep network, and then also propagate the gradients back. So what we can mention here is that most PAC systems are not geared for accelerated analytics as well. So data sharing and acquisition is also problematic because of many different technical or legal challenges. For instance, we can mention that for instance, deep learning, machine learning appliances, like built-in software into some medical equipment, you need, of course, obviously FDA, or in European Union, you need CA approval. Also, sizes do pose a problem, and volumes of these imaging do pose a problem for us in terms of storage or processing. So we have to find an efficient way how to store all these the huge amount of images and quickly process them. Here I give a quick, let's say, figure about how much data we do produce each day, each hour in health industry. So we just can observe, and but this information is also a bit outdated, I think. But in general, this is a huge problem nowadays. Now I'm going to talk a bit in depth about deep learning approach. Why is it so important for imaging? Obviously, nowadays deep learning brings the state-of-the-art performance in terms of generalization performance, first of all, because convolution CNNs or convolutional deep neural nets allow us to effectively extract activation of feature maps from raw images and utilize it when we, let's say, do an inference, and effectively we can learn much more meaningful features and activation maps from these structured data, because filters give a hand a leverage in terms of understanding the data, and without applying a more sophisticated Bayesian approach, for instance. Also, deep learning scales well with the training images, so it takes a lot of time, but you can feed into this huge amount of images. We only do care about how many, for instance, images per second, per watt we can process. Also, bringing more data obviously helps to generalize better. And of course, there is a huge academic and industry effort which is invested into the deep learning field. So a lot of people everywhere around the world are working on this. So for instance, I give a quick example of how we can do image segmentation, medical image segmentation here, and this pancreas segmentation problem. So basically, in the end, you have a probabilistic map where actually your region of interest is located. Now I will talk about the digital pathology showcase. This is our proof of concept project with the University of Warwick. So on behalf of Warwick people, I will talk in depth about also the deep learning architectures and learning strategies, approaches which we do use in this particular project. So basically, why pathology is interested and why digital pathology is interesting by now. So basically, it shows a kind of a sign of a quick digitalization route, because basically you can amend all those huge scale images to some machine learning pipelines and try to extract meaningful features and information from it, learn to some particular tasks and problems. Let's say one of the problems I will be talking about is the segmentation problem. Another one is nuclear detection. Another one is classification. So you see that, for instance, every slide, every image which is being digitalized in pathology is also kind of huge. So usually we are talking about hundreds of thousands by hundreds of thousands pixels. So huge storage demand, about 60 or 100 gigabytes per image compressed. So one particular also thing is that obviously pathologists working with these huge slide decks can be puzzled. So maybe so there are some particular problems, for instance, with this POC when we have to go through some specific proprietary libraries to actually compress, uncompress, so do some pre-processing. So it's also challenging and interesting for us. So again, this project is a joint venture with the University of Warwick, Here we aim only at providing hardware and software solution for inference or scoring only, so we're not talking about training itself. So and here we anticipate that Xeon, Phi and FPGA type of like the processors and co-processors can be interesting for the very fast real-time inference. And of course, will not be providing as a service. Will not be acting as a service provider, but rather we will just make a simple proof of concept, which should be further productionized by someone else. What about software stack? So current solution is based on Python and TensorFlow. There are some proprietary dependencies on MATLAB. Before, they used to work with solely with MATLAB and MATCONNET library. So we are going to eliminate these and push the project towards Intel software stack. So basically, we're talking about here about Intel optimized Python distribution, data analytics and acceleration library, math kernel library, and so on. Obviously, because recently Intel acquired Nirvana Systems, we'll be using Neon engine, so possibly, but this is in our plans. Okay. I will be talking about 3 stages, which which basically constitute the pipeline being executed by Warwick right now. And the first step in this pipeline is the segmentation stage. And here we talk about pre-processing and and segmenting the image into regions of interest. First of all, images are huge, as I already mentioned, 200K by 100K. So here we do 5x reduction. So basically, it's kind of equal to 100x magnification, and we split the images. So we split them in patches, and then we divide them into the training and validation subsets. So patches are quite small, like 60 by 60, 40 by 40. Background patches are excluded by summing the background and processing it and evaluating against some threshold of 90%. So basically, here on this stage, the most lengthy part takes the pre-processing part, because we have to work with these huge images, which are in JPEG 2000 format. And in the end, we generate around 3,000 patches per this huge image. And so basically, we also calculate mean and standard deviations from this, just for the further step. After the pre-processing, we do this segmentation. We feed the batches into the network. Each patch is converted to a deviation and from the mean image. So we basically normalize the patch. It's augmented by flipping and rotating it. And so we basically track the accuracy by the means of the validation set, and export the checkpoints along the epochs of training. So basically the classification, we output classifications. So it's kind of the segmentation stage is viewed from the classification perspective. So we have basically 4 labels for like background fatty tissue, foreground benign, foreground tumorous, and so on. And we optimize everything using normal, quite standard nowadays techniques. This is SGD-based, stochastic gradient descent based with some momentum and higher moments, like for instance the Adam optimizer. Here you see the very simplistic the architecture, which consists of 7 layers, with the final layer being softmax activation along channels. So basically, for each pixel, input pixel, we output the the probability of being one of these classes here. So this stuff is quite typical. So basically convolutional layers with max pooling, with dropout deconvolution again, so such that we can correspond to the initial input image and so on. This was the segmentation stage. Then the output of this segmentation stage is being forwarded to the input of the detection stage, and here the preprocessing looks kind of the same. Detection stage, basically, yeah, again the same images. We are generating patches, performing segmentation before to eliminate all known foreground regions. So basically we're interested only in the foreground regions, tumors, non-tumors, and so on. Also, we are doing the same stuff as in the previous preprocessing step. So basically, patches are a bit differently sized, but still it's the patched approach. The detection stage and the architecture of the neural net looks a bit more complicated, so more convolutional layers, deconvolutional layers, dropout, max pooling, but in the end everything which is being done almost is the same as at the segmentation stage. We are exporting checkpoints, evaluating the model against the validation set, and then we are outputting the coordinates for each input image corresponding to the centroids of the located nuclei. So we are interested in this particular nuclei, and I will show you an image. It's a bit from the different study, but so basically from a different paper from our collaborators from the Warwick side, but approximately the solution is the same. So here we again use cross entropy as a loss, but because we are interested in interlocating the nuclei, so we have only softmax, a sigmoid activation layer. So basically it's scaled between 0 and 1. So basically we output the probability whether this pixel is being a center of the nuclei or not. So here you see the image from this study. So this is the detection study, and here A is the original image. Here the probability maps generated, and here we can see the ground truths being these green regions and predicted nuclei in red. So this approach is based on the kind of the same techniques, which they call spatially constrained CNNs. Where basically you try to leverage the spatial information in your output, basically in your image. So whether your so in these probability maps, whether, for instance, this region of interest is closer to the nuclei or not. So it's quite also interesting and challenging, and in our POC we'll be using this as well. So this was a detection stage, and the final stage is the classification one. Data preparation looks the same, so magnification is a bit less here. We perform segmentation before, perform nuclei detection before that, just to locate patches around these centers. We do the same split in validation and training set. And then we generate these patches. So it's kind of the same procedure as before. And the net itself, the architecture looks a bit similar to the first one, but again, softmax activation along channels. So basically for each pixel, or for each pixel in the patch, we have kind of a probability whether it's one of these 4 classes. So basically epithelial cell, inflammatory cell, fibroblast, necrotic cell, or miscellaneous. So, and maybe size of batches, these sizes do differ, but in general the procedure is kind of the same. There is an augmentation stage where with flipping and rotation. Again, the patch is converted to a deviation from the mean image, which is kind of our baseline. And we export everything, and we output again the classification, so basically the probabilities per pixel in this particular patch. And here you see, for instance, a qualitative example from the same from the same study that I mentioned before, and here we kind of provide a coloring for each particular class. So here there are 3 classes, basically, epithelial, inflammatory, and fibroblast, and we see the magnification everywhere. So this kind of pipeline provides us a good way of examining the image, the huge slide desk, trying to understand where we should look for an interesting region of let's say cancerous region, or where we can find a tumor and so on. So because the output is again the probabilistic maps for each particular pixel here. And that's basically was the end of the our showcase. Here's the legal disclaimer. Thank you very much.
Thank you very much. Questions?
Yeah.
I was going to say, so there's a lot of focus on this using these sort of deep things. What about, do you use like kind of like recursive structures at all? Like recursive neural network structures at all, or not really?
Yeah, we would like maybe to use these recursive like LSTMs or RNNs, but we don't have any kind of temporal structure right now. So basically there is one image, basically, which corresponds to only one time frame, so nothing else. If in particular, there might be other modalities where this is interesting, right? So basically, add additional dimension to the tensor that you're feeding to your to your deep neural net, and there, obviously, the choice would be then LSTM, for instance, as I mean, a layer of LSTMs and blocks where you kind of you're trying to, let's say, get some additional information from this dimension, right? And but for this particular POC, we are not using this.
Yeah.
I've got a question about data, really, and your experience with how easy you found to access the training data. I'm from a company that creates deep learning systems for exactly this sort of thing you've just been displaying. But we found the medical market is the worst market by far, because, as you all know from your deep learning experience, vast amounts of training data is acquired, and the problems with ownership of the data and use of personal data we found to be the major blocker to creating deep learning systems in the medical industry. So I was just wondering, what's your experience of that? Is this the only problem you've applied it to, or have you tried to apply it to others, and are you seeing the same trouble we're seeing with data protection issues?
So yes, it is a massive problem. I think some of it is not technical, it's regulatory, it's legal, and I think some of the good things about being in the UK, for example, that there are databases where large amounts of data is collected. For example, I think Wales, they actually have a very large pool of images, and there are some countries in South America as well where the national system collects all these images. So if you get it down, like for example in the US, it's even worse because every hospital has their own. So having a national system can really help, or some sort of a data sharing agreement. But yes, it is a massive problem, especially if you have the privacy aspects of the people and the data rights and all that. So it's very complicated, and once you've solved that and collected the data in one place, it helps. But some of these new PAC systems, they are getting online. I think one of the main problems getting it from offline to online, so this helps already. Once you have it online, you can collect it more easily.
Okay, Welsh.
Well, I think it's a good starting ground. I think Denmark is another one. They have good.
Danny.
Actually, I had a very, very related question about training data. Do you have a feel for how much you need, or how much, presumably you need labeled data as well, not just the images? How much do you need to be able to be confident about generalization to unseen patients? And
for instance, I can mention this study. So it comes from this one, yeah, from a recent publication from our collaborators, and there, for instance, in terms of segmentation, not classification as here, they needed around 20,000 or 30,000 labeled nuclei to generalize well, and there you can get performance up to like 90 something, 0.90 AUC, so basically something like that. And also, if you're aware what is area under curve, right? And the F1 score was something like 0.8 something. So it's a good generalization, but of course, amount of data, more data, I mean, of course, better generalization performance you get. So
how many patients does that?
So I think this study examined like 10 patients, but the images were huge. Basically, the patches were huge, and they were pre-processed by the pathologists.
But you'd have thought you'd see greater variation among patients. I mean, obviously you see much greater variation among patients than within. So 10 doesn't seem like a very large sample to generalise the population.
Yeah, right. But obviously they noticed that, for instance, for types of cells which were underrepresented, let's say, in these data sets, the performance was worse than for, I mean, it's a typical problem, of course, but like for unbalanced data sets, but usually you observe more data, you get better generalization, because here we are trying to put some additional stuff like augmentation, some different, trying to utilize also the output, let's say spatial structure and so on. So I'm trying to get better performance, yeah. But of course, more patients would, I mean, definitely benefit to the study and to this proof of concept.
Okay, let's have maybe one more question. Yeah.
Yeah. So you have 3 different phases during your training. That is the segmentation, detection, and then the classification.
Yeah. Yeah.
So I'm curious, do you concatenate all the phases together in order to do the joint training of the 3 neural networks, or you just separately train your 3 different phases? And what about your test phase?
Yeah, so they have a hold-out test set, of course, obviously, but it's a pipeline, so it's sequential. It's sequential.
So
yeah.
3 different.
Yeah. So basically, so as I mentioned on the pre-processing slide, so basically you have to evaluate first the segmentation and then detection, and then you can input this information into the final net.
So you have approximately about 30 layers in total of your whole net.
Yeah. Something like that, yeah.
Thank you.
So Nina, is it okay to ask later?
I can ask later, sorry. Yeah.
Okay.
Okay, so let's thank Vilen.
Okay.